Yeah, thanks for the introduction. So my talk is going to be about, it's going to be a showcase of how to apply a geometric method, in particular geometric deep learning, to a problem in medicine or biomedical engineering. So hemodynamic quantities, that means quantities related to the blood flow, like blood pressure or blood velocity, could support prognosis, diagnosis, and treatment planning in patients with cardiovascular disease. So what that means is a doctor could sort of look to an evaluation of the blood flow in a patient and then decide for the proper treatment. And so in hospitals and the clinic, the gold standard of evaluating hemodynamics in a patient is to do some form of medical imaging, construct a 3D model of the patient anatomy, and then run computational fluid dynamics simulation. And for example, in this case here, which is a left main coronary bifurcation, CFD took me 15 minutes on a high-performance computing server. So this might be a problem in practice because setting up the CFD, running the CFD, might be, too time-consuming for the clinical application, and also a hospital might not have a high-performance computing server. So what we propose is to create surrogate methods that sort of sacrifice some of that accuracy that you get from CFD simulation to get faster evaluation speed. So we train graph neural networks on a data set of patient anatomies and ground truth velocity field snapshots. So this is just about trying to relate the anatomy with sort of the steady state velocity field, for example. And the advantage of that would be that all the expensive computations can be moved offline. So we can train sort of once, and then inference for a new patient only takes a few seconds on consumer hardware. Okay, so hemodynamics in biomedical engineering in arteries are usually modeled by the Navier-Stokes equations, but the incompressible ones that you can see here, which consist of the momentum equation, the conservation of momentum and the conservation of mass. And here U is the velocity vector, three-dimensional. P is the pressure, and rho and mu come from the material properties of the fluid. And it's sort of important for our application that we are actually able to relate, just the anatomy of the patient without any other information and without doing explicit simulation of the dynamics to sort of a velocity field snapshot. So this relation has to, we have to be able to kind of find this. And for that, we think that it's actually crucial that we operate in laminar flow, because in laminar flow, the temporal derivative, for example, of the velocity field is tame, and sort of we can assume that the hemodynamics depend in good approximation on the anatomy of the patient, that is to say the spatial operators, basically. On top of that, because usually in biomedical engineering the blood flow in arteries is modeled without gravity, our problem has a certain symmetry. So we would assume that the orientation of the patient, because there is no directional force, does not change the blood flow. It just sort of rotates along intrinsically with the mesh and the anatomy. And this is equivariance symmetry. And basically, this is quite straightforward in CFD, for example, but in neural networks, unfortunately, this is not straightforward to achieve. And one way of achieving this would be to use data augmentation, so show the neural network during training a lot of differently rotated input-output pairs. But a more elegant way is to use equivariant neural networks, and in our case, we use steerable graph neural networks, and in particular, steerable equivariant graph neural networks as proposed by Brandstätter et al. In 2022. Okay, so graph neural networks manipulate and process signals that are sort of defined on the nodes of a graph. And one prominent way of doing this, of manipulating and updating signals defined on the node of a graph, is the so-called message passing algorithm or method paradigm, where we basically look at nodes and then from the surrounding of that node in the graph, construct messages that model the interactions of these two nodes that we're looking at. And the interactions are modeled using this, like, for example, a neural network, psi. And then we just, to update the signal in the graph H, we just have to sort of aggregate all the neighboring nodes and we get our update in each step. And the message passing algorithm and graph neural networks in general are easily applied to meshes because meshes can be seen as graphs by just dropping the information which nodes belong to which volume element, just leaving the nodes and the edges in a mesh. And yeah, there's different kinds of message passing that you can apply. So for example, you have sort of a naive isotropic message passing where your local filters have no sense of direction, just apply the same sort of message to all the from all the surrounding neighbors. And you have anisotropic message passing where your network actually is endowed with a certain sense of direction. And it turns out that the equivariant methods that we're using actually give us some sort of anisotropic message passing, which intuitively should be just a lot better. Okay, so applying the steerable equivariant graph neural networks to our meshes here had one major roadblock, which is that our meshes are very large. Sort of if we would just stack message passing layers in a network, then we end up with problems regarding the receptor field. The receptor field is a concept in deep learning that basically describes the amount of local information that your network is able to accumulate in a single forward pass. So let's say each of your message passing layers, in the forward pass, accumulates a one ring of information from a one ring neighborhood. Then if you would stack, for example, 16 layers, then you would have a 16 ring, neighborhood that your network could access to base its prediction on. And this might be okay for small meshes, but for large meshes, this is like a very inefficient way of growing the receptor field. So how we worked around that is basically by defining some form of pooling. And this works by defining a hierarchy of subsets of sort of the mesh vertices. And then we also have to define a way of projecting from a finer to the coarser point cloud, and also lifting from the coarser to the finer point cloud. And as you can see, so on the deepest level, which is in the bottom right, the sort of neighborhoods are a lot further spaced. So that means that we can aggregate sort of larger receptor fields in a more efficient way, and namely exponentially rather than linearly. Okay. So our steerable neural network, graph neural networks, are composed of message passing layers, and the message passing layers compute messages using fully connected neural networks, and like in particular they're called multi-layer perceptrons. And essentially, if we want this end-to-end equivariance, that we sort of showed at the beginning, if we rotate the input anatomy, then the output vector field should also rotate accordingly. It is actually enough if we just make it so that every linear, so multi-layer perceptron that we use in our messages is itself equivariant. And there's multiple ways of doing this, but how we do it here is we use steerable tensors, and MLP is processing steerable tensors. So, for example, if you have a number of input and output neurons, and you group these input and output neurons in geometric objects. So here, for example, we have vectors and scalars, and at the output as well. But it could also be higher order objects if you wanted to. But the crucial thing is that we know how to rotate these objects. So we know how to rotate vectors, and we know that scalars should not rotate. And sort of with this framework, what we're actually able to is we can impose equivariance via a restriction of the weights of the MLP, of the general function. And there's multiple ways of doing this. So, you can use computer algebra systems if you want. But there's, so SEGNN in particular uses the E3NN library in Python. And the E3NN library in Python implements very nice sort of tensor products using Clebsch-Gordon coefficients. And with these, you can actually build such a fully connected network that satisfies this equivariance. Okay, so then sort of the last puzzle piece in order to achieve the end-to-end equivariant pipeline is that we must describe the shape of each, the anatomy of each patient using only steerable vectors. And one common way of doing this is that people actually, if they sort of have a set of points, then they just take the mean of that set of points and subtract the mean of the set of points. And we do something really similar, but a bit sort of more general for our problem type. And namely, what we do is instead of subtracting the mean of the set of points, we subtract sort of the inlet, for example. So here in this artery, the blood flows in from below and flows out on top. So we can, for each vertex in the mesh, we can compute basically the difference to the closest vertex in the inlet. And we can do the same for the wall of the artery. And here I have cut the artery open for visualization so that you can see the distance is the highest in this on the center line of the artery. And we can do the same for the outlets. And using this, so we basically for each vertex in the mesh we can build 3 vectors like that that describe the shape of our patients. And it actually follows from the definition that this is essentially a way of describing the shape of the patient, which is equivariant to rotations and translations. So it's more specifically, if we rotate the mesh, then the features just rotate accordingly. And if we translate the mesh, then the features stay the same, because we just use relative distances between vertices. Okay, so in this field of estimating hemodynamics from patient anatomy, the sort of gold standard model is PointNet++, which some of you might have heard of. It's a very straightforward, easy to implement model. And we could show that with using SEGNN, with the pooling, the added pooling that we just talked about, we're actually able to beat PointNet++ by quite a bit. So you can see in the first line and the last line by how much. And then on top of that, what we tried is, okay, but what happens if we just take PointNet++ and try to make it equivariant by just learning it, by just using data augmentation, just showing it differently rotated input and output pairs. And we actually found that PointNet++ was not really able to get back to its original accuracy, at least not in our framework. There's probably a way of still making it possible, but we just kept everything the same, the inputs and outputs, and PointNet++ was not able to adapt. But more importantly, we found that we gained quite a bit of data efficiency. So if you look at the plot and read it sort of from right to left, then we trained both of the models, PointNet++ and SEGNN, with progressively less and less samples. And we found that the equivariant method, SEGNN, actually dropped less in performance, and the plot is in log scale if you wonder. So it may not seem like much, but it's actually quite a big difference between sort of the equivariant model that uses symmetry and the model that not uses symmetry. Okay, in summary, we basically built this sort of surrogate method that can be a task-specific surrogate for computational fluid dynamics if you have a lot of data. We handle the large meshes by some sort of pooling, and the method is equivariant to rotations and translations. And how we see these kind of methods used in practice is that, if maybe some people do like clinical CFD trials where they do a lot of CFD simulations and have a lot of different patients available. And then they would have a lot of data that they could sort of put to good use with a method like that, because it's straightforward to apply it on a mesh. And the meshes are usually already there if you do CFD. And what's important in the medical domain is this robustness to misalignment that you get from the symmetry. And also what was nice to see is that we were actually able to extract meaningful information, learn from a small data set by including the symmetry, which is sort of the hope of including these symmetries in your learning frameworks. Some limitations where it's still requires a lot of GPUs to train. this study was based on a synthetic data set, but now we're actually applying it to a real-life data set. And this study was sort of only looked at steady flow with boundary conditions implied in the data set, which is, yeah, maybe you have wondered where the boundary conditions went in a CFD. They actually just kept constant over all the training data, so that's why we don't have to specifically learn them. Yeah, that's it from me, and I'm happy to answer any questions that you might have.
Is there any question for Julian? Okay.
Thanks for the nice talk. So the input is a mesh and the predictions are also on the mesh, not on the interior, right?
I mean, there's two types of meshes. You could have a surface mesh and you can have a volume mesh. So in this study, we actually used volume meshes. So it's a tetrahedral sort of tessellation of the volume of the artery. So this is a volumetric prediction that we do.
Okay.
Here.
And your mesh simplification, is that regular in the sense that you do some kind of downsampling, or do you take into account local curvature or maybe a preliminary estimate of?
No, it's just there's an algorithm called farthest point sampling. So our goal was to have it be as general as possible, and farthest point sampling just works on sort of a set of points. So yeah, it doesn't even have to be a mesh. So yeah, it's pretty standard.
Okay, the reason I'm asking is because in mesh simplification, well, you normally simplify more in the simple regions,
Yeah.
and this you don't do. You just do the
Yeah.
furthest point sampling.
I've played around a bit with mesh simplification, but it's very difficult to get it to work as smoothly as you want it to work, basically. So yeah, I've tried around a bit with it, but in the end, it wasn't worth it. Especially because we don't really need a coarser mesh. We just need a way of passing the messages. We at the end really just need the finest mesh, you know. So because we can compute all these intermediate layers simply by having sort of a set of points and knowing sort of how to connect these points, and we can connect them just by, you know, the nearest few points. So yeah, so
Okay.
but good question, definitely. Like,
And then I was really surprised that the PointNet++ gets worse when you do data augmentation.
yeah, because you also evaluate it on augmented data, basically. So you do the training on augmented data, meaning you rotate the inputs and outputs, and you also evaluate on rotated data. And essentially what it means is, in our framework, the PointNet++ was not able to learn well the rotations, sort of to adapt to rotations.
Okay, thank you.
But I'm pretty sure there is a way of making it, sort of using data augmentation and making it work. For example, maybe you have to train for a lot longer and then it works. So use a lot more weights. So yeah.
Thanks.
So in the framework, Gillian, you often do mentioned modules where you do mean pulling, or max pulling, or mean pulling, I think. Can you explain how you do these? How these layers in the network are precisely done on the meshes, the surface and the volumetric meshes?
So basically, it starts by having two sets of points, so the finer set of points and the coarser set of point, and because you just sample one from like the coarser one from the finer, you can just build sort of local neighborhoods, like pooling, you know, radii, just, you know, by some standard algorithms, and then each point in the coarse mesh or coarse sort of scale has a set of neighboring points in the fine scale, and then you can just take the mean of all of these points and essentially end up with a value for the coarse scale.
And what determines then the neighborhood? What is the metric that you use?
So for each, well, just Euclidean metric. So just for each point, you just take a ball and then you know, determine the neighborhood by all the fine scale points that fall in this ball.
Okay.
But this is actually we're already working on a like more sophisticated, better version of doing this. This is sort of our old methods, and now we do something else. But yeah, I'm happy to talk about that if you want.
Thank you, Julian.
Okay, thank you very much for the nice talk. So let's thank Julian again.